Hello and welcome to today's class. Today I'm going to speak about Poincaré's Polygon Theorem. And by now we know that every Fuchsian group admits a hyperbolically convex, locally finite fundamental domain. And what is this good for? Well, first of all, having a locally finite fundamental domain helps us to understand the orbit space of H modulo the action of gamma in terms of simply performing some gluing between points of the topological closure of the fundamental domain in H. But not only that, having a hyperbolically convex locally finite fundamental domain allows us to compute a set of generators for the group gamma in terms of the sides of the fundamental domain of the convex polygon, which is the fundamental domain. And this can be somehow interpreted that as follows. A hyperbolically convex locally finite fundamental domain allows us to find an explicit generating set for the group, and having this explicit generating set of the group somehow helps us in reverse engineering gamma itself, right? Because then we know that inside PSL2R, so with the relations between elements of PSL2R, the elements of this set allow us to construct the full group gamma. And somehow, if one could actually also have a full set of relations between the generating elements, one could say that one is able to fully reverse engineer the Fuchsian group gamma, right? Because one would be able to present it in terms of generators and relations. Okay, so those are two things that convex locally finite fundamental domains are good for. Now, the Poincaré's Polygon Theorem is some sort of reverse engineering theorem. Sorry. Somehow now one knows that starting with a Fuchsian group, one is able to produce a hyperbolically convex locally finite fundamental domain, namely the Dirichlet polygon, for instance. And with it, one can construct a set of generators for the group. So now we want to go the other way around. Somehow we want to start with a polygon and with some set of Mobius transformations that pair sides of this polygon, and we want to know some sufficient conditions for this data to determine a Fuchsian group as the subgroup of PSL2R generated by this element, and in such a way that the given polygon be a fundamental domain for that Fuchsian group. Right? So somehow, roughly speaking, given certain initial information, certain input information, namely a polygon and a set of side pairing, and a set of side pairing transformations. When does this side pairing transformations generate a Fuchsian group, and when is the polygon a fundamental domain for that Fuchsian group? And somehow Poincaré's Polygon Theorem gives us sufficient conditions. And you see, somehow one can think of this theorem as a reverse engineering theorem, if you want. Later on, we're going to see that actually it also helps us to impose certain additional properties. Like, let's say that you want the orbit space H modulo gamma to have certain specific properties, like for instance, you want it to have certain genus, right, or a certain number of points at infinity, or a certain number of funnels at infinity, and so on. We're going to see later on that Poincaré's theorem allows us to say, okay, I want all these conditions to hold, and then it tells us how the polygon has to look like, or which properties it must have, and the side pairing transformations, how we can take them, or with how much freedom we can take them, and so on. Okay, now it is not the case that if you just give me a polygon and some set of side pairing transformations, that is some set of Mobius transformations identifying sides of the polygon, one always obtains a Fuchsian group. That's not always the case. Why? Well, the main reason, or one of the main reasons, is this angle sum theorem. What this angle sum theorem says is that if you are given a Fuchsian group gamma and a hyperbolically convex locally finite fundamental domain, then at every cycle, at every gamma cycle, so at every intersection of a gamma orbit with the topological closure of the fundamental domain, one always has this equality, namely the order of the gamma cycle times the angle sum must be 2 pi, right? So somehow, if one starts with a proposed set of generators, namely if one starts with certain side pairing transformations, and that is some set of Mobius transformations identifying sides of the proposed polygon, and if one takes the subgroup of PSL2R generated by this set of side pairing transformations, it is perfectly possible that such a relation fails, and this would be automatically saying that the group you generated is not discrete, right? It's not Fuchsian. So, of course, one must find certain conditions both on the polygon and on the proposed set of Mobius transformations identifying sides of the polygon, in order to obtain to be able to reverse engineer a Fuchsian group, or if you will, that the group one reverse engineers is actually Fuchsian. So let's start with the discussion. Remember that at some point we asked this question, which I pretty much just paraphrased, and the question is there a method to construct Fuchsian groups, or a general way of constructing explicitly constructing Fuchsian groups, besides somehow the obvious ones we are able to construct, namely PSL2Z, for example, and its subgroups, or the cyclic subgroups of PSL2R generated by hyperbolic or parabolic transformation, or the cyclic subgroups of PSL2R generated by an elliptic transformation, let's say, the finite cyclic subgroups generated by an elliptic transformation. So far, we don't have such a general method, and today we are going to provide an answer. And I would say it's a quite explicit method. So the discussion is going to be based on this article by Bernard Mastiff, this article in Advances in Mathematics. I'm going to try to adapt my terminology a little bit to his terminology. So in the end, it's going to be the terminology is going to be a little bit like in between the terminology I have been using so far and the terminology he used. Hopefully, there is not going to be much confusion. Okay, so first of all, if you give me a full geodesic, or as I sometimes call a doubly infinite shortest curve. So doubly infinite, because what I mean is that it is infinite in both directions, right? So that is kind of a, would say, complete geodesic, if you will. Take one such, and then a subset is called the degenerate if it's either empty or has exactly 1 point, one element. Now, what is a polygon? So a polygon in the hyperbolic plane is going to be a domain that is an open and connected subset of H with the following properties. That its boundary is a countable union of non-degenerate connected closed subsets of shortest curves. In other words, this boundary is a countable union of segments that are homeomorphic to closed intervals, but are segments of shortest curves, of doubly infinite shortest curves. So, or if you want, the boundary of the polygon is a countable union of segments of geodesics of the hyperbolic plane, and these segments have to be homeomorphic to closed intervals. Okay, so that's the first condition in order to be a polygon. The second condition is some sort of local finiteness of the set of sides. Namely, if you give me a compact subset of the hyperbolic plane, it has non-empty intersection with only finitely many sides of my set D. Right? Where what do I call side? Where is any of these segments? Right? Any of these segments of shortest curves which make up the boundary of D, which constitute the boundary of D. Okay, so this is some sort of local finiteness condition for the set of sides of D. The third condition is that if you give me two distinct sides, then they either do not intersect at all, or they intersect in exactly 1 point, but they never intersect in more than 1 point. And moreover, this when they intersect, the unique point of intersection is an endpoint of both of them. Right? So somehow one side ends there, and the other side, somehow, if you will, it starts in that common point. But it's not like a crossing point in this sense, right? That somehow a situation like the one you are seeing does not happen. The idea is that point of intersection be a vertex of my polygon. Finally, the last condition is that if you have a side of D, so let's say that this is the Poincaré, and if you have a side of D and and it has a finite point as an endpoint, a finite point as opposed to a point at infinity. So if it ends at a finite point, at a point actually in the Poincaré disk, and not in the circle at infinity, then there necessarily exists a different side that starts at that point. Exactly one. Right? So in other words, every endpoint occurs as a vertex where two sides meet. Okay. Notice that we are not yet speaking about infinite vertices. Okay. This we will speak later on. In your screen, underneath my image, you are seeing a part of a polygon, which does not have finite vertices. And the 4 points at infinity that you are seeing, well, you are actually seeing only 3. This I'm not yet calling vertices. Right now, one warning, a warning. Consider, let me draw the Poincaré disk. Yeah, and let's say that I draw, let's say, a quadrilateral. Yeah. So for this polygon, you have these 4 obvious vertices. But you can also say, you can also introduce you see a kind of in the system of sides, you can say, okay, let's say that this is one side and that this is another side. Both contained on the same geodesic, on the same shortest curve. The definition I just gave doesn't prevent you from doing that. Right? So somehow this countable union, you see, is kind of you fix a countable set of such segments once and for all, and it is in terms of that countable set of segments that you define the notion of vertex, of finite vertex. Right? So that for this one you would have 1, 2, 3, 4, 5 vertices. And I do that in order to somehow reconcile with my new notion of gamma vertex. Right? So right now I don't have a gamma, but I do want to allow sometimes such vertex. Okay. So as I said, somehow the countable set of sides is part of the information for being a polygon, and that information is used in this description, in defining what a vertex is. Okay, now, well, this is that set of segments, right? So let's say that this is a polygon and that this is the set of sides that gives me this condition 1, right? So S is countable. And I'm going to define the notion of side pairing for D, or for, let's say, for the pair, if you will, D, comma S. I'm going to be calling it side pairing. I'm going to be calling the notion I'm about to define. I'm going to call it side pairing. And just a warning, Masket calls it identification. But I'm not going to use the word identification in that same sense. Okay, so a side pairing for my polygon with the given system of sides is a pair consisting of kind of the combinatorial side pairing and the geometric side pairing. The combinatorial one is iota, and the geometric side pairing is A. Formally, iota is a function that to each side associates another side of S, another side in S, another side of B, and somehow iota only tells you this side is somehow is going to be identified somehow with this other side, but it doesn't give you more information. It doesn't give you exactly, how the points in one side are actually glued to which points on the corresponding side, iota of the original one, of the original side. This other more specific geometric information is encoded in A. So A, what it tells you is, if you give me a side, A gives you back an isometry of the hyperbolic plane that tells you how each side, how the side is glued to the corresponding iota of T. So more precisely or more formally, if you give me a side T in S, A of T, so the isometry associated to that side of B, map T bijectively onto the corresponding side. Right? So iota tells you which side corresponds to which side, and A tells you how you are explicitly going to glue them. The next condition is that iota be an involution, right? So that if you say, okay, some side is going to be glued to some other side, well, of course, this other side has to be glued to the original one, right? So iota has to be an involution. And moreover, well, of course, we would like that if A of T is telling you how T is glued to iota of T, well, of course, A of iota of T somehow tells you exactly the same, right? But of course, somehow in the other direction. So this condition is only natural. And finally, so some sort of non-degeneracy condition that if you give me the side T, let's say that this is the side T, it has a neighborhood V in the hyperbolic plane. So it's kind of some sort of tubular neighborhood, if you will. With the property that, so here for my picture, let's say that B is here on this side. That when you consider this part of the neighborhood, the part of the neighborhood which actually lies on B, and you move it with the side pairing transformation of corresponding to T, the image doesn't intersect D at all. So that it really moves it completely outside. Okay. Well, I'm already using some terminology, right? So iota is the combinatorial side pairing, and A is the geometric side pairing, and the element, well, it's the element A of T, the isometries associated to the side, are called side pairing transformations. Because those are the actual Mobius transformations that tell you exactly how the sides are glued. And of course, if you give me a polygon, well, of course, with its system of sides, and you give me a side pairing, so you tell me not only how you want the sides to correspond combinatorially, but you actually tell me precisely how the points of sides are going to be glued. Then, of course, I can form this identification space, right, of the topological closure of D in the hyperbolic plane, modulo the gluing, right? Modulo the equivalence relation generated by saying that a point in a side S is glued to a point in a to a point Y in a side T, precisely when well, of course, the sides correspond to each other combinatorially, and the points correspond geometrically, right, which is what is stated here. And I automatically have then this identification map, the topological quotient, and in order to give this star a topology. And now an exercise. So if my identification map satisfies the condition that all its fibers are finite, so that's what this says, that for any point you give me here, its fiber is finite. Then one has then somehow the obvious function defines a metric on this star. Somehow one says, okay, in order to go from P to Q in the quotient, go from one to the other using kind of a finite, like piecewise, using a piecewise geodesic curve, and then see the corresponding length, and then take the infimum over all such piecewise geodesic curves. Somehow that's the obvious function. And what the exercise says is that if pi has finite fibers, then this is actually a metric on this star. And this I'm going to call condition E. We're going to say that V is complete with respect to this side pairing if it satisfies this, so that one actually has a metric, and the quotient space, the identification space, turns out to be complete under that metric. Okay, later on, we're going to find out how to guarantee this condition, because you see somehow the conditions so far, these conditions A, B, D, and E are somehow more or less easy to verify, but this F, because it is harder to verify in explicit examples. So later on, we're going to come back to find a sufficient condition easier to verify. By the way, notice that here I jumped from A, B to D, and I did it because in Maskit's paper, condition C is imposed because he allows orientation reversing isometries here, right? And we are not allowing it. We are not allowing orientation reversing isometries, only orientation preserving. Yeah, and so his condition C is what happens in some cases for when you allow orientation reversing isometries here. Okay. Now you see as I said at the beginning, Um, if one already knows that the subgroup generated by the side pairing transformations is discrete, then one necessarily has this angle sum condition, and where here I'm calling the side pairing transformations the elements of my set gamma star. So of course, uh, if we want if we want the group generated by the element AT, so by what now in this section we are calling side pairing transformations, if we want the group generated by them to be Fuchsian, to be discrete, we have to be able to set this condition about the angle sum has to be satisfied by the subgroup generated by them, right, by the AT. And what we're going to do now is we're going to state that property that has to be satisfied after we take the group generated by the AT, but but beforehand, right? But before considering the subgroup generated by them. In other words, we're going to see how in our current setting with the current information with the information we currently have, how to state the angle sum property that the order of a cycle times the angle sum of the cycle has to be 2 pi. Okay. So start with a finite vertex Z. That finite vertex belongs to exactly 2 sides. Why? Because of condition 4 in the definition of polygon. So it belongs to 2 sides. Pick one of them. Let's call it S. And so we are going to start now with a finite vertex and a side containing one of the 2 sides containing. And we are going to determine 3 sequences. One sequence of finite vertices, another a sequence of sides of D, and a sequence of side pairing transformation as follows. So the procedure is quite simple-minded. So of course we start with Z, with my original side, and with the side pairing transformation determined by that side, by this side. Right? So my first side pairing transformation maps this side onto onto the side that corresponds to it combinatorial. And the picture is this one. Right? So this is my original Z, as you can see here. So this is the side. And then A maps A1 maps this one bijectively onto the side iota of S1, and of course the image of this one is some vertex. Okay. The second terms of the sequences are going to be, well, this is Z2. What else could it be? And then the second side is going to be defined as follows. So this vertex belongs to exactly 2 sides. Again, because of the 4th condition in the definition of polygon. One of these 2 sides somehow already appeared in the process, is iota of S1. So S2 is the other one. Okay, and once we have S2, then we follow kind of the same pattern as at the beginning, which is then we just take the side pairing transformation, the second side pairing transformation to just be the side pairing transformation attached to the vertex. Okay, and we keep going, right? I mean, this process. Now we can apply the same process to this new vertex and to this side, and obtain a third vertex, a third side, and the third Morris transformation, the side pairing transformation. And more generally, we have a recursive procedure, which is that once you have your nth terms of your three sequences, define the next one where Zn plus 1 is the image of the previous one on the corresponding side pairing transformation. Fn plus 1, you define it by looking at iota of Sn and taking the other side. Yeah. So maybe here I should have written iota. Yeah. So this is a mistake. So I should have written iota, and here as well. And once you have your side, then you just take the n plus 1, the n plus first side pairing transformation of the sequence to be the one determined by that side. Okay, so this way we have our three sequences, and well, I have this exercise, which is that if in this case, the three sequences are periodic. So you see here I pretty much just have to apply this one, right? If the fibers are finite, then the three sequences are periodic. It is an easy exercise. Okay. All right. So in particular, well, another exercise is that you see, if you take this sequence, actually any of the sequences, but if you take this sequence, whenever it starts repeating, it actually comes back to the very first member. Okay, so that it doesn't happen that if you start and you start going in the sequence, and then you start being periodic, but that somehow the first vertex doesn't participate in the period. That doesn't happen. That's another exercise. What other exercise? Okay. Now, suppose that D is complete. So it's, as I said, it satisfies. It has finite orbits. Pi has finite orbits. Not finite orbits. I'm sorry. Finite fibers, and I have this one. Well, in any case, the point is that the sequences are periodic. So each one of them has a period, and I define the period of the vertex I started with, the vertex I started with, as the least positive integer that makes the three sequences periodic. That makes the three sequences repeat themselves. Right. So I do this in order not to enter the discussion of whether the periods are all the same, because at least when you allow orientation reversing side pairing transformations, This may not be the same number. The periods may fail to be the same. So I make this definition just kind of to avoid entering the discussion of whether in our case the periods are all the same. But anyway, notice at the moment I have kind of an ambiguity because my vertex belongs to two sides, right? So exactly two sides. One of them is S, but what if you take the other one? So so the exercise, another exercise I leave you is to see that somehow the corresponding sequence of sides somehow both goes in the reverse order, and also the corresponding sequence of side pairing transformations. Right? So that it starts, that is just kind of just the sequence of the inverse. And this one in particular, you see here I have this period, and in particular, if instead of taking this side, I take the other side containing Z, this finite sequence, kind of the representative sequence of for this period, goes the other way around. Okay, so somehow you start with Z1, and then this would be the corresponding Z2, and so on. Okay, so that things are well defined up to reversing the sequences and taking the inverses of the A's. This I leave you as an exercise, and this finite sequence, kind of representing the periodicity, is going to be called an ordered cycle of finite vertices. Now consider the composition of all these A's. I'm going to call it the cycle transformation at Z. So at the end of the class, I'm going to see some examples, so that you get an intuitive idea of how the cycle transformations are formed. And now we can state the condition that corresponds to the angle sum for when we are doing things the other way around, starting with a Fuchsian group and going in this direction, rather than reverse engineering as we are doing now. So my triple, right, consisting of my polygon and the side pairing is set to satisfy the elliptic cycle condition, and then maybe I should say somehow something like elliptic / accidental. If I were to be completely accurate or completely correct, but I'm not going to do it. I'm just going to say elliptic cycle condition if it satisfies E and this other condition. So if the projection has finite fibers, and whenever you give me an ordered cycle of finite vertices, as I constructed here, for some positive integer k, I have this equality, where say this angle is the angle subtended by D at the corresponding vertex. Right? So see that this looks almost identical to the angle sum property for Fuchsian groups. And okay, now about the conditions. So notice that somehow when saying that D is a polygon and this is a side pairing for D. I'm imposing conditions A, B, and D. Then I'm also in the definition of in this definition I'm also imposing the condition E, which is finite fibers, and I'm skipping condition F. I'm jumping to this condition G, and this is just because I can form to form this sum. I only need the finite fibers condition. And okay. Another exercise. Suppose that my triple satisfies the elliptic cycle condition, and then take a vertex, take a finite vertex, and let it be the corresponding cycle transformation, right? The composition of all these transformations that one produces in this recursion here. And take the corresponding integer k, well, prove that actually b to the k is the identity, so that actually b is either the identity of the hyperbolic plane, or it is an elliptic transformation of finite order. So this equality is, I'm going to call it the elliptic cycle relation. We are finally arriving at a statement of Poincaré's theorem. A Poincaré polygon is a triple consisting of a polygon and a side pairing of the polygon, or for the polygon, satisfying that phi, the projection onto this identification space, has finite fibers. The identification space, this star, is complete under the induced metric, and every ordered cycle of finite vertices satisfies the elliptic cycle condition. Notice it is natural to ask for such condition, given the Angelsson theorem that we prove, when working the other way around. And the theorem is that if you give me a Poincaré polygon, and now you take the subgroup of PSL2R generated by the side pairings, then you actually have a Fuchsian group. Your polygon is a fundamental domain for gamma, and moreover, you can fully reverse engineer the group in terms of generators and relations. Now, at this point, there are three issues, three points to take into account. One, of course, the proof. So I really recommend you to have a look at Maskett's paper and what he says about the kind of the existing proofs or the published proofs. So he says a few interesting things without going into technicalities. Another issue is to provide an easy to check sufficient condition for completeness, for the completeness of the induced metric, right? Something that one can actually some sufficient condition that one can actually check just kind of in using D and the original set of side pairing transformations without going, without going into the actual identification space. And the third issue is about generalizations. Let's say to higher dimensions, to higher dimensional hyperbolic spaces, for instance. Let me discuss this condition. So suppose I have the following. So suppose I start with a polygon with only finitely many sides. So the system of sides is finite. Yeah, and then take a side pairing for D. Then, since there are only finitely many sides, of course there have to be only finitely many vertices, right? So so condition E is satisfied. This projection pi has finite orbits, finite fibers. Okay, and then it makes sense to suppose this elliptic cycle condition. So all I'm saying is that in order to be able to assume the elliptic cycle condition, and in order for the elliptic cycle condition to hold, it is not necessary to have a complete metric on the identification space. It is not necessary for the metric I define to be complete. Okay. So it makes sense to impose G, even if we don't know whether condition F holds or not. So completeness of the metric. Okay, now consider the possible shapes of or forms of the sides of D. Of course, there are the finite sides, so that they are kind of the sides of D that go from a finite vertex to a finite vertex, right? And they are homeomorphic to compact to compact intervals. But there are also maybe some sides that are that start in a finite vertex but run to a point at infinity. So those are the kind of the half infinite sides, or what I usually call half infinite. Or it may be that there's a side that is a full geodesic, right? A full short curve. So those that are called doubly infinite. So we have those three types. Okay, so consider the ones that are either half infinite or doubly infinite. Right? So either of this form or of this form. Okay, and you see, so these ones have one endpoint in the circle at infinity, whereas if you give me a doubly infinite side, it has two endpoints in the circle at infinity. And these endpoints I call the infinite vertices of D. Okay, so for instance, in the image beneath my image, you can see that there's at least 3 infinite vertices in that picture. Okay, now take now an infinite vertex and a side containing it. Now it is possible that this infinite vertex belongs to only one side. That's perfectly possible, right? And this is similar to when we have improper vertices that somehow are endpoint of gamma side and the free gamma side, right? Whenever we are given a Fuchsian group, so that's when we were speaking about uh, convex locally finite fundamental domains for a given Fuchsian group gamma, right? So this situation is similar. So it may be that you have your infinite vertex. Uh-huh. So we know that it's endpoint of a half infinite or doubly infinite side of D, but it may be that you see that there is no other side of D ending there, right? So so okay, so that may happen in contrast to the finite vertices, to the situation in the case of finite vertices. Uh, but anyway, you see, take one such Z, a side containing it, and you see, and try to play the same game we played with finite vertices. Right? So this game for producing these three sequences. So of course, the only way to be able to start playing the game is that Z belongs to exactly two sides. And then you start playing the game, and at each step of the game, it is possible that you hit one of these situations, or that you hit this situation of a vertex lying on only one side of D, in which case the game has to stop, right? Because in the recursion here, you really you see you move, and then you take the other one. Okay, it's perfectly possible, but but um, but okay, but so uh, take take all those Z S's where the game never stops, right? So that satisfies that for every vertex produced along the way, uh, you have exactly two sides containing. Uh, okay, that is, if the process never stops, uh-huh, then I leave you as an exercise to show that the sequence is periodic, that these sequences are periodic. I don't see them here, that these sequences are periodic. Uh-huh. And so we can form the corresponding cycle transformation now at my infinite vertex. Exercise. Uh, this cycle transformation has Z as a fixed point. Um, okay, and now we say that our triple, which we assumed to you see to satisfy A, B, D, E, and G. We say that it satisfies the parabolic cycle condition if it also satisfies this F prime, where F prime is that each of these cycle transformations is parabolic. Okay, and the theorem is that if you give me a triple consisting of a polygon and a side pairing, it turns out that I have a Poincaré polygon if and only if the elliptic and parabolic cycle conditions are satisfied. And so this condition is the sufficient condition I was looking for, the parabolic cycle condition. So you see, if you give me a polygon with a side pairing and and I am able to verify that these elliptic and parabolic cycle conditions are satisfied, I automatically know that what I have is a Poincaré polygon, and hence I know that the group, the subgroup of PSL2R generated by the side pairing transformations is Fuchsian, that D is a fundamental domain, and that I can fully reverse engineer the group in terms of generators and relations. Okay, and now I'm going to give you some examples. Consider this polygon that you are seeing here on your screen. It has 1, 2, 3, 4, 5, 6 sides. It has one finite vertex, and that's it. It has several infinite vertices. The combinatorial side pairing is clear, right? So it pairs this side with this side with this side, and this side with this side. Now the geometric side pairing, how is it defined? That one, it has to be like for this side, it has to be a specific Morris transformation, sending this shortest curve to this shortest curve, and so on. And so it is defined. The one I took for the one that is programmed here, sends this infinite vertex to this infinite vertex, this infinite vertex to this infinite vertex, and this sort of Euclidean midpoint. So this point here where you have this transversal crossing to this other Euclidean midpoint here. Similarly, the geometric side pairing transformation, the side pairing transformation mapping this shortest curve onto this shortest curve, send this infinite vertex to this infinite vertex, this infinite vertex to this infinite vertex here, and this Euclidean midpoint to this Euclidean midpoint. Now let's see here. Here you see I'm saying that this side corresponds to this side combinatorially, but that means that the side pairing transformation has to have this one as fixed point. So it has to be an elliptic Morris transformation. And it's then fully determined, right? Because if you measure certain length here from the fixed point along this side, you have to send that point to the point obtained by measuring the same distance here. So there you don't have any choice. Whereas here you see in the first one I took, maybe instead of sending this point to this point, maybe I could have said, okay, send this Euclidean midpoint to some other point, let's say around here, right? And then I would have had certain freedom there. But then in the second one, the parabolic cycle condition would have told me that then for the second one I don't really have freedom, right? But my point is that when you have a side that corresponds to another side and it has a finite vertex, then that elliptic Morris transformation doesn't really have a choice. Okay, now never mind about this for the moment, and let me go to the elliptic cycle condition, right? Because here, I mean, my whole polygon has only one finite vertex, so the corresponding ordered cycle of finite vertices has just length 1. And according to this condition, here, for this vertex here, there must exist a positive integer with the property that the only angle here, which is then the angle subtended by D at this finite vertex, that angle has to be 2 pi divided by this integer. Okay, that on the one hand. On the other hand, we know then that the corresponding Mobius transformation, which then is just this one, you see the elliptic transformation that sends this side to this side. That one is the cycle transformation on my finite vertex, and it has to satisfy this. Right? This is what I call the elliptic cycle relation. Right? So what that is telling me is that the elliptic Mobius transformation that maps this one to this one, which is forced, right, by the combinatorial side pairing, at least in this example, it has to have finite order. Right? So you see, the elliptic cycle condition, which ends up being somehow echoed or reflected here, somehow it is ultimately reflected as the fact that the elliptic subgroups or the stabilizers of the finite vertices of the polygon have to be discrete, right? So somehow that's the significance of this angle condition of the elliptic cycle condition, and kind of the miracle is that somehow this suffices for this being Fuchsian, right? I mean, of course, maybe together with them, with the parabolic cycle condition, right? Now about the parabolic cycle condition. Yeah. So let's say you see here every infinite vertex belongs to exactly 2 sides. So no matter what infinite vertex you take, this game that I referred to a moment ago, that one starts playing similarly to how one plays it in the case of finite vertices, that can be played for any vertex. And so let's see how the game looks like. Okay. So let's say that I start with this infinite vertex, this one here that you're seeing here. Okay, as I said, okay, let's take that one and let's take this side, right? So somehow my initial information, this one, is somehow consists of this vertex and this side. Okay, so the Mobius transformation associated to this side maps this infinite vertex to this infinite vertex, right? And then I change side, so I take this one, the blue one, right? And now I take the blue one and the Mobius transformation associated to this one, the side pairing transformation associated to this side. Okay, it sends this vertex to this vertex here. Right? So, okay, so I'm here, and in this side, I change side, so now I'm here. Okay, and now the Mobius transformation there sends this one here. Right? And so it sends this vertex to this vertex. We are not done yet, right? Because we started here, and now we are here. But now, when you change side, you take this one. So you apply this Mobius transformation. So from here, you end up here with this side, and then you change side. So now you take this one, and then you apply this side pairing transformation, and you are back here. right? So what? So the parabolic cycle condition means that you see this one uh, followed by this one, followed by this one, followed by this one, followed by this one has to be parabolic, right? So let's play the game maybe here. Just kind of it's a bit more clear. So we start with this vertex and this side containing it. We apply the Mobius transformation that sends this one to this one. So we apply, and what we're seeing here is the image of the polygon under that transformation. Um, okay, now at this point we are sitting here, right? And we change side now, yeah, and we apply the side pairing transformation corresponding to this side. We apply it. And what we are seeing here is the image of the polygon under that transformation, which means that the image of this side with respect to this one that sends this one to this one is this shortest curve. So this shortest curve is the image of this one under the composition this followed by this. Okay, now we are sitting here, we change sides, so now we are here, and we apply the Mobius transformation corresponding to this one, which sends it to this side. Okay, we apply it. And what you can see here, you see this one is the image of this one under the transformation I just applied, and this is the image under of this one under the transformation I just applied. Now, what is the image of this one? Well, you see, to do that, I really have to consider. You see, this one goes to this one, so it really is this shortest curve is the image of this one. But that means that if I started with this shortest curve, then I applied this one, then this one, I ended up here, and then this one, and I am here. Okay. Now, where I was, so I started with this vertex, move, so I'm at this vertex, and then I change sides, so I'm here, and then I apply the side pairing transformation corresponding to this side. It sends this side to this side, I apply it. Okay, and then I have to see the image of, I want to find out what's the image of this shortest curve under the transformation that I just applied. Okay, so I do something similar to what I did before, because I know that this shortest curve goes to this shortest curve. So so this one has to go to this one. Under this one, right? On the one that goes from here to here. Okay, but I'm not interested in this blue one, but rather in this orange or yellow one. I think it's orange. Okay, okay. So let's see. So it has to be this one. So what happens? So you take this shortest curve, you apply, you apply and end up here. You apply and end up here. You apply and end up here. So you see the composition I'm interested in, that is the cycle transformation at this infinite vertex, and ends up sending my original side, the first side I took, to this one. Right? And the parabolic condition is that the transformation is parabolic. Right? And now you can ask, okay, so how can it fail to be parabolic? So consider the following. Just so that you see that it may fail to be parabolic. Like, so here is the Poincaré disk, right? And then consider, let's say, consider this. So please forgive the lack of orthogonality. That's not quite easy to draw very well. Okay. Otherwise, I mean, I can spend forever, right? So, okay, and then let's take this one. Okay. And then see, send this one to this one, this one to this one, right? Okay, and let's do it with a hyperbolic transformation, right? So that you send this one to this one with a hyperbolic transformation, let's say, and let's try to draw the axis of the hyperbolic transformation. That may not be completely easy. I don't know. Right. Okay. Uh, okay. So this would be the fixed points of the hyperbolic transformation. All right. But of course, if you take some let's say some geodesy here. When you map this one to this one, like I said, this point to this point, this point to this point, this point to this point, so that you see this hyperbolic half plane is moved to this other hyperbolic half plane. Then you see this one has to be moved to some other one, like I don't know, yeah, so something like this, right? Right, it has to be entirely here, right? So let's say, let's right, and then you see uh, the transformation that ends up. You see, when I consider my transformation as my hyperbolic transformation as sending this one to this one, rather than like starting here, somehow you obtain kind of this potentially deceiving impression that just because it sends this one to this one and this is a fixed point, it is parabolic. But you see, it may fail to be parabolic, right? Because it could be deceiving, and so that is how, at least a priori here, it may be that it could be possible that the transformation that sends this one to this one obtained as the cycle transformation, right, as obtained as a composition of my side pairing transformations, uh, could fail to be parabolic. Okay. Um, so that's the point I wanted to make. Right, and as as as, as I suggested through the discussion I had, the real effect that this that the parabolic cycle condition has uh, has on the actual effect it has, rather than going into the possible discreteness or lack thereof of the group generated by the side pairing transformations, it really goes on to the completeness of the metric of this metric here. And Okay. Now, finally, an example where somehow there is full freedom and one would be always able to deduce that the group is discrete. That the group is discrete and that the metric is complete. So consider this. Take you see this shortest curve, this shortest curve. I declare them sides. I declare them to be sides of my polygon, and let's say this one. This one. I declare them also to be sides of my polygon. So I really have only 4 sides, namely this 1, 2, 3, 4. I have the side, the combinatorial side pairing as suggested there by the choice of colors. Right? So this one with this one with this one. Right. There are no finite vertices. So obviously the elliptic cycle condition is going to be satisfied no matter how I choose my geometric side pairing transformations, right? How I choose my geometric side pairing. Second, you see here, this is all over for when this process doesn't stop for an infinite vertex. Right? So here you see, for instance, take this one. Apply whatever I choose as my side pairing transformation. That I just decide that this goes to this one, this goes to this one, and here you see I take a point and I give it full freedom to go wherever I want here, and something similar here. Right? So this one to this one, this one to this one, and here I take a point and I give it full freedom to go wherever you want. All right. So now you start here and try to play the game for infinite vertices. You cannot even start, right? Because there is only one side it belongs to, namely this one. This one right now I'm not calling side. I'm not calling side of D. Right? So this is it. Right. I mean, according to my previous terminology, this would be a free gamma side. But remember, I'm reverse engineering everything. Yeah. Okay. So really, both the elliptic cycle condition and the parabolic cycle condition are vacuously satisfied. So this means that you see this point, you can send it to wherever you want, and that will be a valid choice of geometric side pairing. And same thing here. This one you can go to wherever you want here, and you are going to obtain a valid geometric side pairing. And the group you obtain is going to be Fuchsian. It's going to have this one as a fundamental domain, and you see the last part, kind of this last part. You see here, this is just the trivial subgroup. So this one is this one is in this case a free group on 2 generators. And now if you compute the quotient space, so you perform the gluing. Somehow it looks like a torus with a circle at infinity, which some people call funnel. Whereas in this other picture, what you obtain is a torus with 1 point at infinity. So somehow geometrically, the difference between this one and this one is somehow the boundary at infinity of in the quotient. Right? I mean, here you have 1 point at infinity in the quotient, and here you have an entire circle at infinity. So, okay, and here you see you have this, you see this point, you can send it to wherever you want, and this point you can send it to wherever you want. So you really have two real degrees of freedom, and so this later on can be said as, you know, the Teichmüller space is two-dimensional. But this we're going to speak in the future, not now.